Welcome PCS members and friends to our today's IBS PCS Thursday seminar. It is a great pleasure to have with us today Professor Hyoungsoon Choi from KAIST. And I would like to invite our scientific host, Alexei, to introduce our speaker. Please, Alexei.
Yeah, thank you, Tilen. So today we have Professor Hyoungsoon Choi from KAIST, who will be talking about two-dimensional quantum fluids in gallium arsenide-based semiconductors. So let me briefly introduce the speaker. So he received his PhD from the Northwestern University in the US in 2007, and afterwards he moved to KAIST, first as a postdoc, later as an assistant professor, and since 2019 he is an associate professor at KAIST. As you can guess from the title, he's an experimentalist interested in various properties of the quantum fluids. And with this, please, Professor Choi, the screen is all yours. You can start.
Thank you. I'd like to start by thanking the organizer for inviting me, and also apologize in advance for having to not being able to stay for like informal discussion after the seminar. I have a parenting duty that I have to attend, and during the COVID period, the child caring duties are a lot more stressful. I apologize for that. Anyway, so as introduced, I'll be talking about two-dimensional quantum fluids today. And at KAIST, I run a laboratory titled Culture Laboratory, which stands for Choi's Ultra-Low Temperature Laboratory. And today I'll first introduce what I mean by quantum fluids. Some of you may know what it is, some of you may not, and some people may have different definition of quantum fluids than others. So today I'll start by giving you the definition of quantum fluids on my part, and then discuss some of the experimental work we've been doing at KAIST. So to the first introduction to quantum fluid when you study physics probably comes in StatMech when you start learning about the quantum ideal gas. So classical ideal gas is usually understood in terms of the Maxwell-Boltzmann distribution. And the classical ideal gas are usually happens at high temperatures. And the typical example would be like a noble gas at room temperature, or almost any like air or most gases at high enough temperatures can be approximated as a classical ideal gas, as opposed to, and these are actually something you learn even like high school or middle school when you talk about the ideal gas law and things like that. Now, things get a little more complicated and interesting when you introduce quantumness into these systems. And due to the different statistics that different particles obey, you have to actually categorize quantum gas into two types. So one is obviously the Bose gas, and the other being the Fermi gas. And Bose gas and Fermi gas follow Bose-Einstein statistics and Fermi-Dirac statistics, respectively, which is something we already know. And what's interesting about these two systems is that at t equals 0, they occupy different ground state. And they stem from the fact that the Bose particle can occupy the same quantum state, whereas Fermi gas, no two particles can occupy the same state. So due to that fact, the Bose gas actually go into this state known as the Bose-Einstein condensate. And it's not synonym, but it's also closely related to superfluidity. However, the ideal gas case, actually the superfluidity actually wouldn't occur. So it's just called the Bose-Einstein condensate. And so that's when all the particles occupy the lowest energy state. In Fermi gas case, the atoms cannot occupy the same state, so they'll start to filling the lowest energy state in order, like in a ladder, from the lowest state to the next lowest state and next lowest state, so forth. And in three-dimensional case, when all the particles go to the lowest energy state, then the system forms what's known as a Fermi sphere in the momentum state, or momentum space, and that would be the description for the ground state. Now, there is a relevant temperature scale in which these phenomena, quantumness, becomes important, and I've just labeled them TB and TF as T Bose and T Fermi, and I'll explain that in more detail later. Yes.
I have a naive question. How about the anyons?
Oh, anyons would they don't exist in 3 dimensions, so.
Yeah, but okay, let me rephrase it. So, I mean, they do exist in 2 dimensions. So, what would happen there at low temperatures? I mean, I also understand that it probably has not been realized experimentally yet. I would be happy to learn that someone did, but still, yeah.
Yes. So, in 2D, the anyons exist, but so what would be the ground state of the anyons? I think it actually depends on the anyon. So, for example, one of the most sought after anyons are the 5-half states in fractional quantum model system, and they are they can be considered as a type of superfluid, but that's not the only scenario. So, and also the currently hotly debated topic of Majorana fermions are also a type of anyons, and they are thought to be again found in some types of superconductors. So but those are not the only cases, but those are probably the most famous examples in the condensed matter system. So I would say they are related to superconductivity in some sense. But all of those scenarios still require some low temperature environment. And
now, of course, essentially what I was curious about is because they're neither bosons nor fermions, I was curious. So they, if I understand correctly, they tend to condense as well.
Right.
They don't behave, they are not repelling each other like the fermions.
Yeah. So I'll actually get to that point later, but even the fermions do condense at low temperatures when you turn on the interactions. So
yeah, well, I mean, unless again there's something I don't know. My understanding is that they simply they pretend to be bosons by pairing.
Right.
Okay. Thanks.
So the closest examples of these ideal Bose gas or ideal Fermi gas would be like the dilute cold atoms, where people have studied Bose-Einstein condensate with. Even that case, like when you get to low enough temperature, the interactions become relevant, and so they're not perfectly ideal on Bose gas, but that would be the closest approximation we can find in reality. And in Fermi gas, actually the electrons in metals are considered the Fermi gas, because the Fermi temperature of these electrons in metals are on the order of thousands or tens of thousands of Kelvin, and room temperature is at least 1 or 2 orders of magnitude colder. So in that regime, actually the Fermi-Dirac statistics of these electrons are important already. Now, so the starting point are basically this. So the quantum fluid, what I mean by quantum fluid is a gas or liquid state whose quantumness quantum statistics become important. as opposed to these classical gas. But like I said, the ideal gas scenarios that we learn in textbooks are not just rare, they actually don't exist. So we actually have to think about real systems, and especially the non-ideal materials with interactions. If the interactions are strong enough, then we actually don't have these gaseous phases, but rather we have a liquid phase. So I either call them Bose liquid or Fermi liquid. And again, the statistics of these systems remain the same, but what's interesting is that the ground state actually changes. So like, as I mentioned earlier, ideal Bose gas are described by Bose-Einstein condensate. But once you turn on the interaction, the superfluidity, the lack of viscosity in the liquid becomes a feature that is pronounced. And also, if you have a set of fermions, the pure ground state should be the Fermi sphere that I've mentioned just now. But once you turn on the interaction, one of the states, ground states that system can find is this superfluidity or superconductivity by a pair of fermions combining into boson-like state. So in this case, the temperature scale in Bose liquid still remains a single temperature scale, but in fermionic case, there is a temperature scale where the Fermi liquid property starts to manifest, and then there's another temperature scale at which the superconductivity appears. And typically this superconductivity temperature is orders of magnitude smaller than this Fermi temperature. And here, when I say Bose temperature or Fermi temperature, physically, what they basically represent is, if you think about the thermal de Broglie wavelengths of a particle, it actually has this 1/√T dependence, meaning that as the temperature gets lower, the de Broglie wavelengths gets longer. And if these de Broglie wavelengths gets close to the interatomic distance, that's when these Bose liquid or Fermi liquid type of behavior start to appear. So because of that reason, actually it is more easier. It's easier to have these quantum fluid behavior if your density is high, because then interatomic distance is shorter. Hence, you get with the shorter de Broglie wavelengths, you get that effect. And also, if the mass of the particle is small, that also helps. And it turns out that because of these reasons, in real systems, traditionally, liquid helium or liquid helium-4 or liquid helium-3 have been the prototypical quantum fluid of that manifests these features. And so historically, people have been calling liquid helium as quantum fluid almost exclusively. But today, I'm gonna just focus on these features, the material that shows these types of features, and if they can be described by these physics, then I'm going to call them quantum fluid. And as we learn in undergrad stat mac, the dimensionality of these systems is very important. For example, if you have a two-dimensional Bose ideal Bose gas or a one-dimensional ideal Bose gas, you learn that the Bose-Einstein condensate doesn't have any transition. It only happens at t = 0 as a ground state. And so these dimensionality of the system can actually change the physics that's being manifest in this system. So one has to think about outside of these liquid helium, can there be systems that manifest these quantum fluid features? And these are the type of materials that we focus on in our lab. And so, as I mentioned, there's, of course, the superfluid helium that I'm interested in. But there are also two-dimensional electron gas and the exciton-polaritons condensate, which is also a two-dimensional system, these two are the main focus of today's talk. And just to give you some idea of the temperature range, as I said, we need some low temperature environment to actually observe these effects, quantum fluid effects. So the superfluid helium-3, to observe superfluid helium-3, we need about 1 millikelvin or lower temperature. And for two-dimensional electron gas, we typically work with tens of millikelvins to a fraction of a Kelvin. And I'm going to skip the electrons on helium part. And the exciton-polaritons condensate, so it happens that the relevant temperature scale is actually somewhat higher. So, like I said, the dimensionality is important, and one way to achieve these low-dimensional quantum fluid, in my mind, is to use these gallium arsenide-based systems. And the basic idea is that if you stack aluminum gallium arsenide or aluminum arsenide with gallium arsenide, there is a band gap difference between these semiconductors. Different semiconductors have different band gap, and that band gap actually creates this potential well or potential wall for the valence band and conduction band in this gallium arsenide region. And in this well, you can actually have a very tight confinement of the particles, so electrons here and holes in the valence band. And that tight confinement can actually serve to limit the particles to stay just in this surface between the layers. And so, and also, if you actually dope these system, you can get even stronger confinement. And the way it works is that if you have this band gap, and then let's say this is dashed line is your Fermi energy, and if you dope this system with silicon, it raises the Fermi level near the doped region, but this Fermi level actually gets enforced with or equilibrates with the rest of the system. And when that happens, you actually get this band bending. And if you layer this aluminum gallium arsenide, silicon doped aluminum gallium arsenide with gallium arsenide, which has smaller band gap, and then you have this region where there is a very narrow potential structure, and within this region you can actually highly confine your electrons, and you can basically, depending on how shallow or deep this potential is, you can actually confine just the lowest energy electronic states along the z direction, and it becomes a flat xy plane electron system. So those are the type of system that we're interested in. And as a first part of the experiment, I'm gonna today talk about controlling quantum vortices in these what we call the exciton-polaritons condensate. And the stuff that I'll be talking about can be found in these two published results. And this work was done in collaboration with all of these people shown here. So the one former student and one current student are the main driver of these works, along with two of the people from Professor Hyoungsoon Cho's group at KAIST. So this is so these people are people from KAIST, and I'm pretty sure some of you know Professor Soo-hyun Gong, who's at Korea University right now. And then the sample that we use were provided by the people from KIST, so Mr. Han Kyu Kang and Susok Kang and Seok-in Kang and also Dr. Jin-Dong Song grew the sample we used for this experiment. And then I'm pretty sure you you know these people here, Dr. Ivan Savenko, Dr. Meng Sun, and Mr. Do-Gyun Ko, who provided the theoretical description of our experiment. So first, the sample that we use for this experiment is what we call a microcavity exciton-polaritons system. So it has a substrate, and then there is a alternating layer of aluminium arsenide and aluminium arsenide, and the index of refraction change basically limits the forward propagation through the destructive interference. And so by stacking these two material in layers, you can actually create a mirror. Yes. Sergey?
So here we have no silicon in the sample, just because you have rapidly switched from this description of 2D electron gas in the sample due to the skew quantum well due to silicon and this sample. So these are the different things here.
Yes. This is just relying on the difference in the band gap, and we're basically confining the electrons and holes in these gallium arsenide layer. So this isn't doped sample.
Okay, so more or less standard sample.
Yeah, this is a standard sample. So
okay.
I may have misled you, but I was referring to two different types of system earlier when I was saying that you can either layer gallium arsenide and alum gas, or you can also dope it to have a confine. So if you don't dope it, you basically have these electron hole pair system which you can create to use bosonic particle in this, or you can dope it and make it either electronic system or a hole system, depending on how you dope it. So that's the idea. So in this case, system is not doped.
Okay. So here's the standard exciton of electron and hole, and okay, the previously, right. Yes, it was purely for the electron. Yeah, thank you.
Right.
Thank you for clarifying this.
Yeah. So here, so this is a mirror, and there's another set of mirror. So these two mirror pair actually can confine the light in this region that we call a cavity. And then within a cavity where the light intensity is maximum, we actually stack these gallium arsenide so that the exciton production is most effective. And in this case, the microcavity energy or the frequency of this or the photon energy of the light that kept in this microcavity is in this region. And we actually use 720 nanometer laser because there is this dip in reflection, so that we can actually transmit light to actually go into this cavity. And when you shine basically light here, you get these electron hole pair from the absorption of the laser, and then the electron hole pair couple to form the exciton in semiconductors. And that exciton once again couples with the light trapped in this microcavity. And so this electron hole photon composite particle is what we call exciton-polaritons. And it turns out that there is a coupling between the exciton and the photon, and you can see it by having this anti-crossing between the exciton dispersion and photon dispersion, and then you get lower polariton branch and upper polariton branch. Yes.
Question? Yeah. So can you explain, please? I see here three kind of comp structures of this gallium arsenide in this picture. So why do you have three of them? Where precisely is your exciton excited or trapped? In which of these? I see three kind of comp or substructures. Yeah.
Okay, so the reason is because when we have light trapped in the cavity, we get these three antinodes in here. So we want the regions of antinodes to be where these quantum wells are placed, because that's where the excitons are going to be formed by absorbing the laser. And we just have, we try to put as many quantum wells as possible in a region of these high intensity to strengthen, this is just to strengthen the signal.
I see. So they are formed, they can be formed in any of these thin, dark gallium arsenide stripes.
Right, right. So
now, what happens once you have many of them? Will there be some non-trivial interaction between them, or is that something which is between different stripes, so to say, different layers, or is that not
different layers are more or less non-interacting?
Fair enough. Thank you.
Because they're still a few nanometers apart, and it's still, the separation is larger than the wavelength, so they don't have any meaningful overlap. And this sample is placed in a cryostat that can be cooled down to a few Kelvin, and then we shine laser, and that laser goes into the sample, and then once the exciton-polariton is formed, it actually eventually decays because the lifetime is finite, and we basically observe that decayed light. And what's good about the exciton-polariton system is when the light emits, it actually carries the information about the exciton-polariton. And that photon, by imaging the real space distribution of the intensity, we can basically look at the density distribution of the polariton. And by going into the Fourier space through a lens, we can actually convert the real space into a Fourier transform and go into the K space, which gives us the momentum distribution of the system. And also, you can put this photon into a monochromator and look at the energy spectrum. And depending on whether we look at the energy spectrum in K space or energy spectrum in real space, we can actually get the spatial distribution of energy or the dispersion relation of this energy, which is this example here. And also, by carrying out an interferometer experiment with this emitted beam, we can also extract the phase information about the wave function. So we can actually directly map the phase of each part of this wave, which is kind of cool. So what are we going to do with this system? So one of the key feature of a superfluid is that a ground state wave function is just a single wave function because they are all in the same state, and you can basically describe it with the density and phase. And what's interesting is that if you calculate the current density, it turns out that the current density is proportional to the gradient of the phase only. So if there is a phase gradient, you get a flow of superfluid, which is what we call superflow. And so you can define the velocity of the superfluid with this gradient of a phase position-dependent phase. So it's a scalar function. So you can, from the simple vector calculus, you get that curl of this velocity has to be 0, which means that superfluid must be irrotational. And you can see this effect by actually trying to rotate a can of superfluid. For example, if you have a can of liquid helium-4, and if you try to rotate it, it actually won't rotate until, oh, and another thing is that until you actually get to some what we call critical velocity, then the can actually exert enough angular momentum into the system. Then the liquid superfluid should be forming a circular flow. But in that case, because of this wave like feed property of the superfluid, the velocity looped around a circle should actually, because the wave function should be single valued, it has to be actually quantized. And that's this h bar over m is what we call a quantization of a circulation. And that, but because the superfluid should be irrotational, because the curl of V should be 0 everywhere, for this condition to happen, what happens is that there has to be a core where the superfluid gets depleted, where the superfluid density goes to 0. And this is what we call a quantum vortex. So when the superfluid gets a rotation, the rotation is supported by actually creating a core with a depleted superfluid. Now, if you try to rotate this faster, of course, you can create n to be just any integer, and that was the Onsager's prediction. However, later on, Feynman found that it's actually more energetically favorable to split a vortex into multiple singly quantized vortices instead of having a one large multiply quantized vortex. And so these are actually observed in the classic superfluid helium-4. And this experiment was done by actually a system that resembles this. Now, this is a what we call a dilution cryostat. It's about a 2-meter tall refrigerator, and you actually rotate this entire cryostat to create these kind of quantum vortices in the superfluid helium. Now, it seems very ineffective, and so it's not a very it's very technically challenging experiment to do. So there are also other ways to observe these quantized vortices, and that is to chain the system to atomic BC. And obviously, you can see these quantized vortices in these systems as well. And so it happens, if you have this exciton-polariton, and exciton-polariton is a particle of electron, hole, and photon. So if you think about the total spin of this composite particle, it's actually a boson. And if you have large enough number of these exciton-polaritons at low enough temperature, then one would think that maybe it could form these condensate. However, it's a two-dimensional system. And I said earlier, if you have a 2D system, then there's no finite transition temperature. However, I think this is not perfectly settled. But if you ask me, the reason why we can see these kind of quantized vortices in exciton-polariton at finite temperature is because it's actually not a system of infinite size. This is actually a very small scale system. It spans only across a few micrometers. So we don't have to have a long range order. We can only have like a quasi-long range order, and that's enough. So in this case, you can actually, it is observed, these quantized vortices are observed in this exciton-polaritons, and there are multiple different methods that people have adopted to create these vortices. And the reason why these such complicated method exists is because unlike superfluid helium or cold atoms, where the constituent particles are just permanent objects, here these exciton-polaritons are artificially generated composite particle in a semiconductor. So you have to create exciton hole and combine photons to it. And those combination also have a finite lifetime. So you actually have to, this whole thing involves the process of generating these exciton-polaritons and a process of condensing these exciton-polaritons to the ground state. And sometimes you can actually create these polaritons and the condensate simultaneously, which is typically a method of the resonant pumping. And there is a non-resonant pumping, which is you excite electron holes at very high energy, and then you wait for those electron holes to relax and combine with photons and form the polaritons. And if you have high enough density of those polaritons, then you can get into this condensate as well. So what we tried to do was so the previous method they weren't actually a controlled method of injecting vortices. So we tried to think about a way to just inject one vortex at a time. And the method that we adopted was that we start with a laser which has an orbital angular momentum, and those are called the Gaussian Laser. And what they have is they have basically the wavefront that is spiraling, and the amount of spiraling wavefront actually dictates the amount of orbital angular momentum of the laser. And we thought that we can actually transfer the orbital angular momentum to the polariton system. Then maybe we can create the quantized vortices in this system with a definite orbital angular momentum. So and we also tried it with a non-resonant pumping by injecting energy into this electron hole plasma at high energy, and then wait for it to relax and form this exciton-polaritons condensate at the dispersion minimum of the lower polariton branch. And somehow the method actually worked, and so we shine the Laguerre-Gaussian beam, and here this is the profile of the reflected laser, and we see a clear donut-like shape because of the circling wavefront, and there is a hollow core. And here the interference pattern shows this fork-like pattern or Y-shaped pattern here, which represents the 2 pi phase winding around this core. So it tells us that you can see that there is a orbital angular momentum corresponding to L equals +1. Now, when we have low intensity, then the polariton that emits the light has no feature. But when we have high enough intensity, which we call above threshold intensity, then we get this core, hollow core, and also a 2 pi phase winding, which is a signature of the polariton actually carrying these orbital angular momentum. This was actually, and to confirm that this is actually a condensate, we actually look at the angle resolved photoluminescence. Yes, question, Sergey.
Yes, yes. I had a question. So you tried to realize the of resonant pumping with the reservoir, but still you want to imprint vortex, not using SLM, but using this of resonant scheme with the reservoir. Yes.
Yes, right.
Okay, so well, yeah, it just to check that I have understood well. So and here for me it's some kind of novelty. Okay, thank you,
Yeah.
Thank you for clarification.
And so also to make sure that we have a condensate and not just, oh yes, Do-gyun.
Yeah, so I have question. So below threshold, when we have this energy dispersion, it shows only in lower polariton branch. But why do we see nothing in upper polariton branch?
You mean
so like in figure.
Yeah. So the exciton reservoir usually lives on this lower polariton branch.
Yeah, all right.
So when they relax, it stays in the lower polariton branch, and just by excitation, we rarely see upper polariton branch.
I mean, so we start with the non-resonant pump with in high energy, and then the particles relax down, but the particles never go to the, I mean, like upper polariton branch or something.
They probably do, but probably the lifetime is too short, and we don't see it.
So there is some possibility that they still there, but just like most of them just go to the lower polariton branch. Okay.
Yeah. During the relaxation, there is actually a bottleneck here, which keeps the exciton reservoir in this lower polariton branch. So that's probably most of what we observe. Yes, Sergey.
Sorry, I mute myself. So is the reservoir rotating, or you do not know? Is the reservoir rotating? Because as far as you are using the light which carries angular momentum, well, I could imagine that the reservoir is rotating, and the reservoir who is rotating can also provide some angular momentum to this ground state in the lower polariton branch in the center.
Yeah, so that I'll get to that point later a little in more detail, but the answer is that there is a minute portion of reservoir that is rotating.
Could you repeat, please? I didn't catch. Excuse me.
So it's not the whole reservoir is rotating, but there is a very, very tiny fraction of the reservoir that seems to be rotating.
Okay.
That's actually what Ivan and Do-gyun calculated and told us. We'll probably get there later. Anyway, so here, just to make sure that we have a condensate instead of just some polariton liquid, we look at the dispersion curve, and below the threshold density, we see that there is a very clear-cut parabolic dispersion. But once you have high enough intensity, these actually go into a certain momentum state close to P equals 0, and that's one signature of the condensation. And by changing the orbital angular momentum of the light to be +1 or -1 state, so this is the phase winding of the laser. And when we look at the emission from the polariton, we see that the phase winding actually follows the phase winding of the laser. That was unnecessary. Sorry about that. And also, when we inject the Laguerre-Gaussian beam of L equals 0 and L equals 1 and L equals 2, we see that the quantized vortices actually increase by the same number. And here we see the effect that even though we inject L equals 2 orbital angular momentum, the resulting state is 2 singly quantized vortices instead of one doubly quantized vortex. So these are all interesting, but the question remains, which is related to what Sergey was asking earlier, just now, not earlier, just now, about whether the reservoir is rotating. Because earlier I said the whole process relies on forming electron hole plasma, and that relaxes down to this exciton reservoir, and then forming exciton-polaritons, and that condenses down to the ground state. And there's a whole chain of relaxation process that is involved, and this is an open system in terms of the particle number, because it's not a conserved system, because due to the finite lifetime. So it's not obvious that this angular momentum should be actually conserved throughout all of those processes. And it's a bit, actually, it was a bit of a surprise that it actually worked as well as it did. And we wanted to figure that out. Excuse me for 1 minute. Oh, sorry about that. Anyway, so we wanted to figure out what the process was involved there. So what we did was first, actually, so earlier, if we look at the earlier I've shown you the spatial dispersion, spatial energy spectrum. Actually, I've shown you the dispersion, and you can look at the energy versus spatial distribution, and it kind of looks like there are two different energy levels. And what we did was, oops, sorry about that. So sorry. So there is an energy level, two different energy levels. And what we wanted to do was we actually wanted to extract the phase information for two different energy levels separate. So what we did what we call the energy tomography, and we basically took the slices of image in the space energy space, and then collected them into a three-dimensional map, and then sliced through the energy cut, and carried out the real space map and phase space map, and this is the result. And what you see is that this high energy state actually carries this angular momentum, and the low energy state actually doesn't. So what this seems to imply is that even though the system has orbital angular momentum, it's not the entirety of the system that carries the orbital angular momentum, but only a part of it. And you can change this ratio between the high energy state and the low energy state by changing the diameter of this Laguerre-Gaussian beam's wavefront. So if it was this donut-shaped ring laser, and you change the diameter of this donut, and you can see that if the diameter is small, you only see this ground state. And as you increase the diameter, you get to see this excited state develop. And so there's certain range of diameters where you have both of these states. And we wanted to make sure that we wanted to check whether they were simultaneously happening or sequentially happening. So what we did was we did a time resolved measurement of the system. And so for example, at 5.2 millimeter micrometer diameter laser, what you see is that before about 40 picoseconds, you see this excited state and the ground state at the same time. But after about 50 picoseconds, the excited state actually vanishes. And if you look at the 6.3 micrometer experiment, you see this excited state gradually shifting down to this ground state with no angular momentum. And if you have a fairly large diameter, like 7 micrometer or larger, it seems that within the lifetime of the exciton-polaritons, it remains more or less on the excited state. So what this seems to tell us is actually the angular momentum is actually cascading through the high energy state to low energy state. And the lifetime of this angular momentum carrying state can be controlled by the diameter of the pump beam. And it was somewhat unexpected, and we reached out to Ivan and his team to help us figure this out. And so they carried out this driven dissipative Gross-Pitarevsky equation-based simulation. And they actually imposed that there is 2 types of reservoirs: incoherent reservoir, which doesn't have any information about this orbital angular momentum, and a very, very tiny fraction, I think about thousandths or 10,000ths of the total, which we call a coherent reservoir, which has this angular momentum. And that very, very tiny fraction of the reservoir, when it condenses, actually serves as a seed. And because of this quantum coherence of the superfluid, this tiny fraction that comes from this coherent reservoir seems to be enough to populate the whole system to have this orbital angular momentum. And then over time, because of as the exciton reservoir falls, the system actually, the energy landscape changes. And through that process, you eventually end up in the ground state. And that's what we found. And those are the results that are reported. And to summarize, the point is that one can control this superfluid vortex in exciton-polaritons system using the Laguerre Gaussian beam, even using them non-resonantly. So even if the system involves a lot of relaxation process, it somehow conserves the angular or preserves the angular momentum information of the incident beam, which is generated in the condensate. And I only have about 5 or 6 minutes, but so let me go through the second part of my talk real quick. And this is a work carried out through the collaboration at the SRC Center we have at KAIST, which is the Center for Quantum Coherence in Condensed Matter. And the main contributor of this work is my student, Thomas Park. And theoretical support was provided by Professor Hyoungsoon Sim's group at KAIST. And actually, Professor Hyung-Choi and Professor Yoon-Chul Chung are the two main figures that actually help me wet my feet in these two-dimensional electron gas system. and their students were also involved in this project. And the sample that we used for this experiment was provided by the Weizmann Institute. And so this is the silicon doped sample that I mentioned earlier. And the main question is Fermi gas description valid for these two-dimensional electron gas? And the answer is yes. Actually, it's a very well-known problem. And one of the ways to find this out is using the technique called magnetic focusing. And the basic idea is that you eject electron from this slit, and then you collect that through this slit by actually forming a cyclotron orbit of this electron. So when the orbit and the cyclotron orbit matches the spacing between these two slits, then the electron will be collected. So you can actually measure the current from this end to see whether electron is flowing or not through these two slits. And the cyclotron orbit always carries the information about the electron to mass ratio. So that's that can be used to find this information. And one question we had was when we do this kind of experiment, the energy of the electron that is ejected here is changed by the bias voltage that we supply here. But when the electron gets ejected, this slit actually doesn't filter out a single energy level. Because when the bias voltage is applied, this slit that we call quantum point contact will actually allow any electrons with the energy smaller than below this bias voltage. And it was somewhat odd, it seemed somewhat odd that we were able to actually exactly find the effective mass to charge ratio based on this simple non-interacting system for this single energy value. So what we wanted to do was use a quantum dot instead of a simple slit. And the reason is a quantum dot has a, due to its three-dimensional confinement, it actually has a distinct energy level. So if we raise the energy by applying the bias voltage, but if there is a quantum dot in between, only the energy that matches the level at this quantum dot will get sent out here, and that can be collected in this at this point. As opposed to the quantum point contact, as I alluded to earlier, it actually, even though it's a slit, but along the traveling direction is actually dispersive. And so you don't actually get a single energy. So here the experiment was to use the quantum dot to send out a single energy hot electron and see if that gets, how that electron energy is related to the magnetic field that we're applying. And the cyclotron radius have this relation here with the applied magnetic field and the momentum of the orbiting electron. So here is the result. And actually, if we use the quantum dot, one of the problem is that to change the energy level of the quantum dot here, we have to use what we call the plunger gate. So you have to change the plunger gate to shift these energy levels in the quantum dot up and down to match the bias voltage that we're supplying on the reservoir here. But when we apply magnetic field to quantum dot, this energy level can actually have a slight shift because of the orbital motion within the quantum dot that's rather complicated. So when we actually fix the plunger gate voltage and carry out a magneto-focusing experiment, they don't actually represent the maximal line as the line drifts like this. So we actually had to map the whole plunger gate versus magnetic field profile, and then follow this line through which the magnetic focusing, the plunger gate value at which the magnetic focusing happens. And we compare this to the case where the QPC experiment was carried out. And what's interesting here is that if we apply the magnetic field, there is a peak at which the electron current gets maximum, which is when the cyclotron orbit matches the spacing between the slits. And as we increase the bias voltage, we see that this peak shifts linearly with the applied bias. And this is because the magnetic field for the cyclotron radius is proportional to the momentum of the system, which is proportional to the square root of the energy. And here the energy is the energy of the electron, which can be considered as the Fermi energy plus the bias voltage. And if the bias voltage is small compared to the Fermi energy, you can approximate it with this linear relation. And that's exactly what we're seeing here. However, when we did the experiment with the quantum dot, we saw somewhat unexpected result. So this straight line is this relation that we expected, but the energy of the magnetic field of the system seemed to deviate from this expected line. So this was somewhat weird, because if we thought it is a simple Fermi gas, then this result should be more well following this structure for the quantum dot case, but that wasn't the scenario. So we looked into this feature in more detail. So this is the simple straight line for the quantum point contact scenario, and this is the deviation in the magnetic field. And we also measure the broadening of this magnetic field transmission line, and we see that as the bias voltage increases, there's a little change for the quantum point contact scenario, but for the quantum dot scenario, there was a pronounced line broadening. And Professor Hyoungsoon Sim's group provided us a fairly simple model. So the idea is that a quantum dot doesn't have a single energy level in there. There is a multiple energy levels. And when the electron actually gets ejected, the other electron levels that are occupied in the quantum dot can actually have a Coulomb interaction. And if we limit the current of the ejection, basically we can think of a time scale, which is the inverse of the 1/t would be basically the time scale for, on average, one electron gets ejected to produce the amount of current. And within that time scale, we can think of the electron that dwell time within the quantum dot. And once it gets ejected, we impose that this electron can actually have a Coulomb interaction with the remaining electrons inside the quantum dot. However, if this electron is far enough away from the quantum dot, the reservoir here would basically shield the electron from the electrons of the dot. So there has to be some length scale within which or beyond which the electron gets screened, and we basically set that length scale to be a few nanometers to about 10 nanometers. And if we divide it by the Fermi velocity of the electron, then we get basically the amount of time this ejected electron can interact with the quantum dot here. And that we set that interaction time, and then our estimate actually turns out that both of these times are actually very, very shorter compared to the time scale of the electron ejection. So most of the time, the interaction doesn't happen, but for a very brief period of time, there is an interaction. And that interaction, basically what it results in is that it can actually excite an electron in the quantum dot to a higher energy state. And that energy should basically be lost from the ejected electron. And so it happens when the electron energy is close to the Fermi level, these electrons don't have basically enough energy to excite an electron from the Fermi dot to a next level. So for low energy bias, there's little to no energy loss. Whereas as you increase the bias energy, these ejected electron has actually a lot of room to fall, and that actually gives us this energy loss. And there are more details of this experiment, of this model, but due to lack of time, I'm just going to show you the experimental results compared to the simulation based on the Professor Sim's group's model, and they are actually fairly consistent. So although that wasn't our original intention, it turns out that we basically found a length scale within which an electron interacts with a quantum dot, and that interaction actually is the reason why this electron didn't seem like a Fermi gas or Fermi liquid initially. But if you take that into account, the electrons in gallium arsenide 2-dec are actually indeed a very good Fermi liquid. So with that, I conclude my talk today, and thank you for your attention.
Thank you, Professor Choi, for presenting these very interesting results from your lab. Let us thank our speaker. And we have time for maybe a few short questions. So perhaps let me start in the first set of experiment with polariton excitons. So what was the maximum number of vortices that you've been able to detect? Was it 2, or did you kind of try to push it as far as it goes?
We've only gotten to up to 2 because we haven't managed to generate the Laguerre-Gaussian beam with higher orbital angular momentum yet. So it's one of the things.
So the light is the problem, not the.
Yeah, light is the problem at the moment. Mm-hmm. Now, once we have the light, it could be that the sample is also the problem, but we don't know yet.
Mm-hmm. But you are still developing. Trying.
Yeah. We're trying to develop these laser that can have a higher orbital angular momentum, because we actually want to see these Abrikosov vortex lattice in this system as well, with very large number of vortices. But
okay.
But it's challenging. So one of the directions that we're taking this is to actually explore the vortex dynamics in many directions. Like, forming vortex lattice, or measuring the Magnus force, or observing like a vortex Hall effect, things like that. But it requires some engineering in the light front.
Okay, thank you. Very exciting. So we're looking forward to more news from the lab. Okay, we have also a question from Dogyun. Kodo, please.
Yeah, so at the really beginning of your presentation, so you show us the structure of microcavity.
Yes.
And then there was like the pairs of the, I mean, in the meters. And as far as I remember, the number of the pair was different, like 16 and 20. Is there some specific reason why you guys set as the different pairs?
Oh, so well, in theory, the more the merrier. But as the sample gets thicker, the quality becomes harder and harder to control. So it's harder to have too large a stack on the top layer. So this is basically the sample with the best sample quality we could get. So currently we're trying to develop something like 40 pairs and 30 some pairs, but we haven't had much success.
Okay. Also, it's still quite confusing about just like to create a polariton in microcavity. So when you also show us the structure, the band structure, and then pumping the non-resonant, the inactive reservoir. So you was mentioning the exciton plasma. So I always
electron hole
like
plasma, yeah.
Electron hole plasma. And
right.
so in quantum well, so there's a electron hole is trapped there in the quantum well in the middle of the microcavity. So when you shoot the laser, the pump, so this pump will generate the electron hole plasma. Is it true?
Right.
In the quantum well.
Right.
And then the process to polariton condensation occurs like that inside the quantum well, or?
Can you repeat the last part?
I'm just such a confusing. So I only understood the pump will generate the electron hole plasma inside the quantum well. And then this electron hole plasma will change to later polariton condensate. Yeah, I just know in the theories like there's some energy relaxation and scattering. This is I only understood. But I mean, in real life, in microcavity, what is really happening? I'm still didn't understand well.
Oh, so what's happening is here. So in this dispersion curve, there is a high energy excitation of electron hole plasma, which will relax down in energy, and it will get collected here on the dispersion bottleneck and form exciton reservoir. But there is also a large amount of photon in the cavity that can couple to this exciton, then that will form the exciton-polaritons. So this exciton has this, this is the exciton energy level, and this yellow curve shows the photon dispersion curve in the two-dimensional plane. And if there is a strong enough coupling, then this exciton and this exciton reservoir will couple with the photon, and then that anti-crossing will basically form two different dispersion branches, which one we call lower polariton branch, one we call the upper polariton branch.
Okay.
But most of the time that the resulting polariton will have lower energy and hence will be collected in the lower polariton branch.
So we always talking about this reservoir stuff. So when you also solve these cross-fit equations, but we can also think about this reservoir, like inside the microcavity. I don't know. Is that really exists, like some inside microcavity, or?
Right. So it'll exist in this gallium arsenide layer, in this gray shaded stripes.
So okay, we can think about, the reservoir really exists in this gray. Well,
right.
Okay. All right. So that's I always wonder about. Thanks.
And Sergey?
Yeah, yes. And what is the lifetime in this sample? Maybe I have missed this information.
Oh, the lifetime is on the order of 10 picosecond-ish.
10 picosecond. Okay, and just to know how many years old is this sample?
How old?
Yes.
Oh, we've been using the same sample for like 7 years, I think.
Okay, and I have a question also. Are the vortices which you have shown in the results, are they pinned to some defects of the sample, or they are rather free?
They're free. We actually, so sometimes they're pinned, but we try to find the region where it doesn't get pinned.
Okay, and is the second part of your talk published somewhere? Again, maybe I have missed this reference,
yes.
but if possible,
yes.
can you please move to the reference?
Sure. Yeah, it's published in the Physical Review Research.
Okay, here. Okay, yeah. Thank you.
We have a question also from Sergey.
Yeah, thanks for the nice talk, and follow up on the question by the other Sergey, which is if the vertices are free, are they kind of like rotating also then, or what is the dynamics?
Well, so I've actually skipped a lot of those discussion, but spatially, the laser that we use have these donut shape, and in reality, this is the resulting polariton density is also, and exciton and polariton density is highest around this ring, and that actually generates causes this blue shift in energy, and that actually serves as like a potential wall. So this isn't actually completely free. So in terms of the potential profile in real space, it actually has some profile like this that traps these polaritons in here. So it's free to move within this trap, but there is some large trap that holds the whole polariton condensate within finite region.
Right, but then if it is free to move within this well, how does it move?
Oh, then the core is more or less fixed, and then the polariton superfluid just rotates around that core.
And so you showed, I think, results with up to 2 or 3.
2, yeah.
2. How far can you go further on? Can you go up to a lattice, a vertex lattice, or is that not realistic?
That's one of our goals, but like I said earlier, we haven't had success in generating the laser itself with large enough orbital angular momentum. So 2 is the the maximum we can do at the moment.
And can you maybe then recall again, what about other experimental groups, maybe with other schemes of exciting these vertices? What is the record there?
So there are cases where a large number of vortices are observed, but here they do it with a no net angular momentum. So the total angular momentum of the system is conserved. So they actually get this vortex anti-vortex pair. So this is a in some sense a lattice of vortices, but with net angular momentum 0. And what we want to do is create a vortex lattice with a total net angular momentum with, you know, n equals say 7 or 10 or some non-zero but not infinite number.
I see. Okay. Thank you.
And we have also comments and questions from Olga in chat. So let me read. Olga says, thanks for the great talk. Small questions regarding second part. How much energy levels are involved in the dynamics? And what is the energy width time scale of an energy level of a dot?
Right. So the energy scale, so the relevant energy scale is the Fermi energy, and it's on the order of about 10 millielectron volts. And the experiment that we carried out here goes to about 1.5 or 2 electron volts. So and the length scale, like I said, was of a few nanometers, and with the Fermi velocity of what was the value? Fermi velocity is I can't remember it off the top of my head, but this total time is a few hundred picoseconds, and this T-tune is about tens of about 50 picoseconds. And it turns out that this T interaction over the screening length of about 10 nanometers is on the order of 50 femtoseconds. So this is extremely short. So most of the time, the electron doesn't see the quantum dot, but within that short amount of time, we get this energy relaxation. And the reason why we know or why we think that is such a short range interaction is because if we change this distance between the slit, the amount of energy relaxation doesn't change, meaning that the energy relaxation doesn't happen through the most of the time it travels, but it happens during a either initially or near the end of the process. But the QPC, the difference is QPC versus quantum dot, so it has to be near the quantum dot, and that's what the model also consistently provides.
Okay, Olga, I hope this answers your questions. Do we have any further questions from the audience? Olga says thank you. And it seems we have exhausted all the questions. So let us thank Professor Choi again.
Well, thank you again for inviting me.
And